Okay, so picture this. You're on your computer, you've got music playing, you're scrolling through a website, and then bam, a notification for a new email pops up. All of it happening at once, totally seamless. Your computer is just juggling it all. But have you ever really stopped to think about how it's doing that?
I mean, how does it keep the music from stuttering while the web page loads? How does it make sure that email alert doesn't just crash the whole system? It honestly feels a bit like magic, doesn't it? But it's not.
Well, the answer is a critical piece of software humming along in the background, the operating system, or what we all call the OS. You can think of it as the real brain of the operation, the master manager that's pulling all the strings to make that digital magic happen. So how does it actually pull it off?
To really understand how the OS does its job, you gotta see it as the master conductor of a huge, complex digital orchestra. And it really boils down to 3 core responsibilities that let it manage everything so perfectly.
So the OS is basically juggling 3 main gigs all the time.
First, there's abstraction. This is where it hides all the complicated hardware stuff from your apps. So when you hit save, you don't need to know how the disk drive works. The OS handles that translation. Second, resource management. It's the ultimate scheduler, deciding which program gets to use the CPU, the computer's brain, for any given nanosecond. And third, protection. It puts up these digital walls around every program. So if your browser crashes, it doesn't take your whole system down with it.
Now, our modern operating systems are, brilliant at multitasking. But it wasn't always this way. Not even close. To really appreciate what your computer is doing right now, we've got to take a quick trip back in time, to an era when computers could only think about one thing at a time.
Early systems, like the infamous MS-DOS, were what you'd call single tasking. You could run a program, and that was it. You had to wait for it to be completely 100% finished before you could even think about starting something else. Super simple, sure, but man, was it inefficient. And here's why that was such a big problem. A computer's CPU is blazing fast, right? But it was spending most of its time just sitting around, twiddling its digital thumbs, waiting for some slow operation, like reading a file to finish up. So some geniuses came up with a clever solution called multiprogramming. The idea was simple. If one program is busy waiting, the OS just instantly switches the CPU's attention to another program that's ready to go. No more wasted time.
This was a total game changer for efficiency, a massive leap forward. But as computers became more interactive and personal, solving that one problem ended up creating a brand new, even more interesting challenge.
See, it's one thing to switch between completely different applications, like flipping from your web browser to your music player. But what about all the different things happening inside a single app? Just think about a word processor for a second. How can it possibly be checking your spelling in real time while you're still typing new words? If the whole application was just one single task, that'd be impossible. And the answer to this little puzzle is understanding the difference between 2 really important ideas: processes and threads. Okay, so a process is basically the application itself. Think of it as the whole program running in its own protected bubble with its own private memory. It's heavyweight because it holds everything: the code, the data, the whole shebang. A thread, on the other hand, is a lightweight little worker inside that process. You can have lots of threads running inside one process, and the cool part is they all share that same memory.
The best way to picture this is to imagine the process is an entire kitchen. The threads, they're the individual chefs working inside that kitchen. You've got one chef chopping vegetables, that's the app responding to your typing. Another chef is stirring the sauce, that's your spell checker running in the background. And maybe a third is plating the food, that's the autosave feature. They're all in the same kitchen, sharing the same ingredients, the memory, but each one is working on a different task at the exact same time.
So having all these threads, all these chefs, is amazing for making an app feel responsive. But having all those chefs running around the same kitchen at the same time, well, that introduces some serious risks. And our master manager, the OS, now has some brand new, really tricky problems it has to prevent.
The first major problem is something called a race condition. And it's exactly what it sounds like. It's when multiple threads are literally racing to read and change the same piece of information. And the final result ends up being a total mess because it all depends on the random, unpredictable order they finish in. It can lead to pure chaos.
Let me just walk you through how easily this can go wrong. Let's say we have a number, x, and its value is 5.
Thread A comes along, reads X, and calculates that X plus 1 is 6. Simple enough, but before it can save that result, the OS switches control over to thread B. Now thread B also reads X, which is still 5, remember? So it also calculates that the new value is 6. Then they both save the result. The final value is 6. But it should have been 7. An entire calculation just vanished into thin air. That's data corruption.
The second huge danger is something called deadlock. This is basically a digital standoff. It's a traffic jam where two or more threads grind to a total halt because each one is waiting for something that the other one is holding on to.
So here's the classic deadlock scenario. Thread 1 grabs resource A and says, "This is mine, and I'm not letting go of it until I get resource B." But at the exact same time, thread 2 has grabbed resource B and is saying, "Well, this is mine, and I'm not letting it go until I get resource A." They're just stuck, frozen in a circular wait, unable to move forward forever unless the OS steps in to break it up.
And this is where the OS puts on its traffic cop hat. It gives programmers tools like something called a lock, which works just like a key to a shared resource. Only the thread that's holding the key can make a change. So only one chef can use the salt at a time. By managing who gets access and when, the OS prevents both these race conditions and deadlocks and keeps all the digital traffic flowing smoothly. So you can see how the operating system went on this incredible journey. It evolved from a simple, one-track mind assistant into this incredibly sophisticated conductor. It's now managing a truly dizzying number of tasks all at once, protecting them from each other and making sure every bit of your computer's power is being used to its absolute fullest.
So, to recap, we've seen how the OS is truly the master manager of your computer. We saw it evolve from that clunky, inefficient, single-tasking world to become a master of multitasking. It juggles whole applications, which we call processes, and all the little tasks inside them, which we call threads. And maybe most importantly, it protects us from the absolute chaos of parallelism, stopping digital traffic jams like deadlocks and race conditions so it can conduct its incredibly complex symphony.
You know, when you get right down to it, the real magic of the OS is that it's a master of illusion. It gives every program the illusion that it has a gigantic amount of memory all to itself. It gives you, the user, the illusion that dozens of things are all running at the exact same time on a single processor. It expertly bends reality to give us a perfectly smooth, seamless experience. And all of this leaves us with a final, pretty big question. Today's computer processors have dozens, sometimes hundreds of cores. Our demand for doing more things at once, for more parallelism, is just exploding. So what new, even more complicated kinds of race conditions and deadlocks are waiting for us out there? What new mind-bending puzzles will the next generation of operating systems have to solve? It seems like the conductor's job is only going to get